we were beginning our discussion of how we generate what we call non-classical light. And what we said, the way we've defined classical light to this point is light whose state is describable as a statistical mixture of coherent states. And such fields arise from sources if those sources, if the quantum fluctuations of those sources are negligible. And we treat them as just a mean field, a classical current. And so we needed to get beyond that somehow. And one way to think about that is what are the kinds of currents that are produced in nonlinear optics. Okay? So in order to discuss that, we just began by introducing the ideas of nonlinear optics. And what we're looking at is the situation in which we have some material, we have some dipole response, and that dipole response is no longer describable by the Lorentz oscillator model. Okay? Lorentz oscillator model is a charge on a spring. If you pull the spring hard enough, it's going to be nonlinear. Okay? Of course, so that's why nonlinear optics was developed concurrently with the invention of the laser. Because when you had intense enough fields, you were distorting the material enough for the material to have a nonlinear response. Okay? It's strong, but it's not necessarily that strong. And so generally, we looked at the dipole response in a power series in the amplitude of the field. So we talked about there being a first order response we call chi1, a second order response chi2, chi3, et cetera, et cetera, et cetera. I mean, you'd expect these coefficients if we're in this perturbative regime, that these higher order effects become increasingly less and less important. Now it turns out that for reasons that are not clear in the way I've written it, chi2, although it would be the first nonlinear effect, in order for the materials that have a chi2 response, they can't be inversion symmetric. There's a parity symmetry because of the fact that really this is a vector, and there are two vectors here. So if we have inversion symmetry, this is not going to fly. So, for example, a gas of atoms doesn't have a chi2 response. It has a chi3. And that's what we often live off of. What Andy's going to live off of for his thesis. But a crystal that doesn't have inversion symmetry can have a chi2, and that's the strongest nonlinear effect if you can get it. Right. So, if in the linear optics case, again, this is just kind of a schematic. Really, we should look at this in the. This is really an expression in the frequency domain, not in the time domain. So, in the frequency domain, the polarization density that oscillates at frequency omega is proportional to the electric field at that frequency, with the proportionality constant being chi1 susceptibility. If we go beyond, so in that case, as we know, that if you drive the system at frequency omega, it will, in steady state, radiate at omega. So in linear optics, you don't generate any new frequencies than were already present. Okay. On the other hand, if we have nonlinear effects, we do get other frequencies, or we can. And even in steady state. And so the process that we were looking at involves when you have a chi2 type nonlinearity. If you look at two powers of the electric field at frequency omega and omega 1 and omega 2, the beat between them can produce another frequency that's either the sum or the difference between those. So that ends up being what we call a three-wave mixing process at frequencies omega 1 and omega 2 and omega 3. So if we call those three frequencies as such, so that omega 1 plus omega 2 plus omega 3, then we can look at the interaction between three waves that have those frequencies. We treat them as plane waves with slowly varying modulated amplitudes. Okay? And we derive from the Maxwell's equations what the equations for propagation of those amplitudes were. And there are all kinds of different nonlinear processes that can come out. For example, if we inject the two frequencies omega 1 and omega 2, then we would generate the sum frequency. If I injected the frequency omega 3 and omega 1, and this was satisfied, then I would generate the difference frequency. And as we discussed, it was important in order for this process to be efficient in the transfer, as efficient as it can be, in the transfer of energy between these waves, that we had this phase matching condition, that the wave vectors also added together. And that was tricky business. We'll come back to that. So one important process, one that we're going to return to in a few weeks, again, we'll talk about more also today, is this process of optical parametric amplification, whereby one has a strong pump field and one wants to amplify another field by transferring energy from the pump into the signal. Okay? So I inject the pump and the signal, and if I satisfy these conditions where omega 3 is now the pump, omega 1 is the signal, then I will have I choose this to be the case, then I will generate I will both amplify the signal as well as generate a new wave at the wave vector propagating direction ki, which is the difference between k pump and k signal, and whose frequency is the difference between this and this. Okay? And that is what's called parametric amplification. Okay?
And the choice whether you get a sum or difference depends on the angle in which you...
No, so it depends what I input, right? So if I put in both of these, but not this, then I generate the sum. Okay? If it's the case that there is, I have to phase match, and as we said, that required, in this case, well, so it depends on those directions and how the indices of refraction at those frequencies for that direction of propagation, for that polarization, etc.
So the phase matching determines...
It does.
Okay.
Right. Okay. So that was our nonlinear optics 101. Maybe 101, maybe 102. I don't know how far we got. So what we're really interested, the reason for doing this was to understand the quantum optics of this, not the classical optics of this, necessarily. So let's look at the quantum problem now. Get some charts. So, quantum version. So again, our Hamiltonian for the problem now as a quantum Hamiltonian has the form, if we treat our current as the dipole current, so that's like a minus d dot e, in this case, polarization current. That's our fundamental Hamiltonian, where these are now quantum operators. And the resonant pieces of this, the pieces that will have the strong, so kind of the rotating wave approximation, involve the matching, so that all the frequency, we don't have fast oscillating terms. So this is the rotating wave approximation that we've discussed before. Okay. Now, so let's look at the situation where we've driven the system into steady state so that the material response is proportional in some way to the fields. Okay? So we can look at the same kind of situation that we did classically, but now with the quantum operators. So let's look at linear optics, expressed in this way. So my positive frequency component here if I want, well, let's write it out. I don't know how to say this. Let me just write it roughly for the moment. I'm being vague about whether this is in frequency space or in time space. Okay? But that's basically what we got. Okay. Now, remember, so my positive frequency components here, let's get rid of the meat here. Let's write this out as we had before in our quantization volume. And again, let me just ignore for the moment, although we really can't. It's important, as we saw in phase matching and the whole shebang, the vector nature of the field. But to get some of the key ideas, I want to ignore that for the moment. Okay? So allow me that. All right? So that's my positive frequency component. It involves the annihilation operators. And the negative frequency components involve the creation operators. Okay? So now I plug that in here. What I see is that, again, I keep, in the linear optics, everything is at a particular frequency. So this is really, for each mode, there's omega at that frequency, and there is a chi at that frequency, pardon me. And I'm going to get things like a dagger here and a here. Here I'll get a dagger and an a here. But of course I can then just commute it, and that's just a constant, and I don't care about it. So at the end of the day, for linear optics, my Hamiltonian will have the following form. It's going to be, something like, let me keep some of my notes here. So this I'll write generically in the following way. Sum over some pairs of modes, which I'll just label I and j, some little coefficient hij, ai, dagger, aj. It will have that generic form. Okay? Where these I and j here label modes such that, in this case, the magnitude of ki equals the magnitude of kj, so that the frequency is the same. They don't have to be in the same direction, though. Is that clear? Where that's coming from these products. And my coefficients here, hij, is the integral over my material. Could, you know, it has chi1 in some region of space, and then I have all these coefficients. So, what can we see about this Hamiltonian? Well, the Hamiltonian, first of all, conserves the total photon number if I assume no absorption. And that's clear from the fact here I annihilate a photon in some mode, and then I create it in some mode. So the total number of photons is conserved. And because I assume linear optics here, the mode, the number of photons of a given frequency is also conserved. Okay? So the linear interaction conserves I should say non-absorbing. Of course, I could absorb photons and just turn them into some other form of energy, but we're talking about the moment transparent, real chi1. Conserves photon number with a given frequency. So the effect of this Hamiltonian is really just scattering. Okay? So linear optics, photon scattering. The unitary evolution that's generated by this is really just the scattering matrix. If I take my evolution, the photons coming in from minus infinity and going out in time positive infinity. This is going to have the form where this parameter theta is generally complex, and it's just given by this hij parameter times t. So this theta ij is hij times delta t over h bar. Where delta t might be, for example, in 1D, the time it takes the light to propagate over the length of a piece of glass. Okay, that's the interaction time. So, what does this transformation do? Well, there's kind of two kinds of interactions depending upon, and we can look kind of diagonalize this matrix. What you would see is that in linear optics, if I looked at the transformation of the unitary transformation of some in mode, this is what I call the out mode. That this is equal to sum over J, some matrix lambda ij and we solved this problem in, these are my in modes. We solved this problem last semester in homework. This lambda matrix is none other than the scattering matrix of the modes. So for example, suppose I have a beam splitter. And I can send in light into, classical light into two modes, right? So I have in the output field will be a transformation, a linear combination of these guys. So E1 out is equal to the transmission of E1 in plus the reflection of E2 in, etc. I mean, my lambda matrix in this case is trivial. T, assuming it's a symmetric beam splitter, I have a transmission amplitude on the, right? Reflection amplitudes. So, the effect of linear optics here is just to scatter the waves around. Of course, I could scatter both into the same, and if you notice if I equals J here, then that's just the rotation operator that we studied in phase space. That's a phase shift. So basically, all that happens in linear optics is photon scattering, and an example of that are the eigenstates of the scattering operator. Those are the scattering phase shifts. So we can have photon scattering, which could be change mode or phase shift, an existing mode. That's all that can happen. That's linear optics. You can have focusing of beams. Of course, that is, you think about that in terms of the phase front being shifted and then the rays. You can have things bouncing off, going in different directions, but that's all that can happen. It seems pretty clear from this that if I started with, and this is another thing we studied, you should review in your homework. If I send in coherent states in, I get coherent states out. Linear optics does not change the photon statistics. Okay? It's important. So if I look at the unitary transformation on a set of modes with the displacement operator, I get the displaced in other words, the classical amplitudes get transformed just as in classical optics. The vacuum fluctuations get carried away or carried around for the ride, but they're not in any way modified. So linear optics seems like it's pretty useless from the point of view of quantum optics. Now we're going to come back to that because there are some major surprises. There are fairly recent major surprises about what you actually might accomplish with linear optics if you maybe add some other elements to the problem. For example, photon counting. Or you don't inject coherent states. You inject Fock states into the problem. But you still have linear transformations. It's not universally powerful for kind of quantum processing, but there have been some major surprises, and they're fairly recent in history, like last year, a couple of years ago. All right. But if we want to get that non-classical light, we're not going to get it with linear optics. Linear optics does not change the photon statistics. So now let's look at three-wave mixing. Okay, so we'll look at that again. Let's look at this where we have our three waves. We have our pump, got some coefficient. It's got an annihilation operator to pump the signal. And the ether. Phase matched. Sum of these guys equals that, and the sum of this Now, of course, one way we can understand phase matching, and it's often described, is energy and momentum conservation. Because we put H bars here, then there's something about the energy of the pump photon being equal to the sum of the energies of the signal in either photon and the momentum of the pump photon being equal to the sum of the momentum. This is a little subtle, and it's not exactly, I think, correct to say that this is momentum conservation. Because the momentum of the wave inside a dispersive medium is a little bit subtle. It's not really just related to the index of refraction. There's issues of the group velocity and so forth. But yeah, we can think about where momentum conservation land. It's often stated that way. So those are our waves. So again, we have polarization here. And we have polarization at different, let's write down the phase match processes. So with this configuration, my Hamiltonian will have the following form. There'll be some constant times something at either the I, then this guy, right? That's phase matched because that has an e to the minus I omega pump, and this is e to the plus omega signal, e to the plus omega either. And then the conjugate term. Okay. Now, of course, really my Hamiltonian doesn't know, I mean, as far as the Hamiltonian goes, there's an infinite continuum of different waves that satisfy this phase matching condition. Okay? So in principle, I really need to integrate over all the frequencies and wave vectors, and I can keep the ones that are phase matched. Okay, but right now I'm just got one term in that general integral. So what we see is that the three-wave mixing process involves these three photons. The two signal photons, or I mean the signal photon and the idler photon and the pump photon. And in particular, what we see here is a process by which we annihilate a pump and create a pair of photons, one signal and one idler. So the three-wave mixing process involves, depending upon what I had here in the signal, I couldn't. This would correspond, for example, to some frequency generation. Whereby I annihilate omega s and omega I and create together a big fat chunky omega p, or a situation where I annihilate omega p and create these two. Okay. And of course, if I put this field in and that field in, then what I'll do is annihilate this, amplify that, but in the process of amplification, I also create the idler. So all of those processes are seen in this kind of Hamiltonian. Okay? Now, as we discussed in the classical case, when we're talking about the kind of parametric amplification case, so if I have an OPO, or OPA, the optical parametric amplifier that we discussed in the classical case, typically the pump is very strong. And the annihilation of a photon at the pump will be negligible compared to the other signals. In fact, we might have vacuum coming into the others, in which case it's certainly the case that if we had a very strong pump, that the change of the photons of the signal idler would be huge compared to any change in the pump. So when that's the case, we have some, we might say that the input pump in a coherent state and it's got some classical pump amplitude, that as always we can write our pump creation operator as some classical field plus a fluctuation around the mean field. That's equivalent to making the Malo transformation that we've discussed before, a unitary transformation, taking the coherent amplitude out of the state and putting it into the operator. And these quantum fluctuations around the pump will be just negligible if this is huge. So we just neglect this. This is equivalent to the non-depleted pump approximation that we discussed last time. So under that circumstance, my Hamiltonian will have the form some constant kappa signal idler some constant, call this one kappa star, call this one kappa. Okay, so that's my approximation in the non-depleted pump approximation for those two particular modes. Okay. Now, suppose, let's consider the case degenerate collinear phase matching. So we're going to look at the case where everything is chosen just right, that this is the pump, and the signal and idler are in the same mode. So the omega signal equals omega idler is half the omega pump. Okay? It's the inverse of second harmonic generation, subharmonic generation. And K pump, K signal is equal to K idler. It's equal to half the weight vector of the pump. Yeah?
Does there need to be another dagger on the Hamiltonian?
There does. Thank you. Sure does. Yeah.
This is also, I don't know, a little bit tangential, but I couldn't help but notice that that looked kind of like the James Cumming type Hamiltonian, but with, two, pairing two different annihilation operators. And would you, if you injected just like a single pump photon, would you get something that looked like Rabi oscillations between, like vacuum Rabi oscillations between having one signal photon?
Right. So I think that's more the situation of the linear optics case. So
okay.
There is, I could look at this as there is a formal equivalence between spin and two modes of a harmonic oscillator. Something which I don't remember if we had a harmonic or not, but we sure will if we have it, which is the Schwinger representation.
Okay.
So the Schwinger representation is a way of saying there's Jx, Jy, Jz is some combination of these two modes. It's really a matter of, mapping, if I have spin up, spin down, second quantized, I can think of that as annihilating a spin down and creating a spin up.
Yeah.
Right? That's kind of right. And there's this formal equivalence there. And so there is, as we studied last semester, the rotation of a polarization on a wave plate, on the Poincare sphere is Rabi oscillation.
Okay.
So they're formally equivalent.
Okay.
Right. Okay, cool. So what were we doing? Oh yeah, we forgot our dagger, it's back now. And now we're talking about the degenerate case. And so in that case, for the degenerate collinear OPO, or OPA, I'll come back to the OPO in a moment. My Hamiltonian has the form kappa A squared plus kappa star A dagger squared, where A now is the annihilation operator for the mode, the subharmonic mode, okay, which is the signal and the either are the same mode in this case. Okay, so A dagger creation operator for mode at omega is half the pump. K is half the pump. Well, everyone smiles because they notice that what that is. If I look now, what is the time evolution operator that's generated by this? It's the squeezing operator, right? This is the squeezing operator with the parameter zeta, e to the zeta over 2, or zeta over 2, a dag, or a, the star should have been here because it's better. Minus zeta star over 2. The dagger squared, where zeta is equal to kappa over 2 times I times the duration of interaction, which is the length of the crystal over C. So, what we have shown is that the process of three-wave mixing with a strong pump generates squeezing. In fact, the way that one typically generates squeezing is through this process of three-wave mixing, picking out particular modes by making them resonant inside an optical resonant cavity, which is in the jargon known as an optical parametric oscillator. So what one does is the following. You have your Chi2 crystal, you have a cavity here. The cavity is resonant at the frequency, so I send in, so this is the pump, it's transparent to the pump goes right through. But it's resonant for the sigma. That rattles around. That's the guy that has the strong interaction. And then you want to get it out, so you put some kind of bow tie thing here with a partially transparent thing. And at frequency omega, what comes out? Squeeze vacuum. Because we put in, what's coming into this cavity here, we have the vacuum. If we didn't seed this with any light at half the pump frequency, all we're doing is squeezing the vacuum fluctuations through the three-wave mixing process. So 2 photons here. So what we end up doing, to lowest order, but this is squeezed vacuum. And that squeezed vacuum is vacuum and some amount of 2 photons. Right? We're creating photon pairs through spontaneous parametric downconversion. That is to say, we started with a pump photon, and through this process, we spontaneously created a pair of photons, and actually multiple sets, depending on how big that is. And those photons are in superposition with the vacuum, and that is our speed. Yeah?
So does the squeeze vacuum come out at some special angle?
Yes, indeed. So, what determines the quadrature along which we are squeezed? Well, what determines that is the phase of the pump. So this, but this is a complex parameter zeta. We remember what actually is here, if I wanted to be correct about it, was, you know, we can just look at that as minus, you know, square root of 2 zeta star. Right? So that parameter zeta was our squeezing parameter, our complex squeezing parameter. The magnitude of that determines the amount of squeezing. Okay? And of course, it really, the length here now depends on not just going through the cavity once, but the fact you bounce. I mean, there's some factor, I don't know, some real optics person can tell me how the finesse of the cavity comes in here, but it's in there somewhere. But the phase, the quadrature along which you're squeezed, depends on what kappa was. And I swept all of that under the rug. Kappa was proportional to the pump. And the pump has an amplitude and a phase. So the phase of the pump determines the phase of the quadrature. So if you were to do a balanced homodyne by, so how would I do it? I mean, I think you do it kind of like this. I send in a strong omega. I have second harmonic generation. Which generates a pump at twice omega. Okay? So the phase of the second harmonic is coherent with the phase of the initial thing. I then use this, I have a beam splitter. It's not even a Theorist beam splitter, it splits it right. And I bring this back around with this and have a local oscillator and look at the beat between those. And as I change the phase of this, I will see my noise dip. Does that make sense? All right. So, what are some of the main lessons to take away from this? One is that linear optics doesn't change photon statistics, but nonlinear optics does. Or as it can. And it's because, in some sense, the linear optics is really a one-body effect. Each photon does something, but it does something independent of the other photons. Whereas in the linear optics is kind of a many-body effect. And it's through those many-body interactions that we change the statistics and can make them non-classical. And in particular, what we just saw here is the simplest such example, the example that comes from the first non-trivial non-classical effect, which is squeezing, which involved these, this kind of pair creation and pair annihilation. Okay? Now, I should say that, you know, we started with the three-body effect, right? We started with the pump, the signal photon, and the either photon, and they did something together. And we got rid of the pump photon by basically going to the mean field approximation for the pump. In some sense, we linearized our effect to the first non-trivial effect. So squeezing, as you will see in problem 1 of the next assignment, comes out of any time I have any many-body effect. If I look at the first non-trivial correction to linear optics, it'll be squeezing. Okay? So a chi-3 interaction would also have squeezing. Right? A chi-3 interaction might have the following thing. I might have this. So this involves 4 photons, right? It's a 4-wave mixing process. This is what we call, in optics, the Kerr effect. The Kerr effect is the fact that the index of diffraction has a small effect that depends on the intensity of the light. So this, and if you linearize this, I write every as delta, I call this B. This is the difference between the two. And you keep only terms quadratic, you're going to get a B squared and a B dagger squared. So anytime you linearize about a mean field, the first non-trivial thing you get is squeezing. Yeah?
So do the other higher order effects sometimes ruin your squeezing, or do they just do other things?
I think they do things we would like to have, but are hard to get. So, and that sort of leads into what we're going to talk about now, and into the rest of this lecture and next, which is how non-classical is squeezing really? In a sense, it's non-classical in the sense that we defined it to be non-classical, in the sense that it can't be a state that is produced by a classical mean field current. But what we really want to say in some sense, and we're going to elaborate on this throughout the semester, the question, what does it mean for something to be classical versus non-classical? How do we define that? Why? How is that operationally meaningful rather than just a definition? And squeezing, as we'll see in a little while, is only marginally non-classical. So those higher order effects, we sure would love them. They're just hard to get at because of the fact that they're weak. So first, it's just hard to get photons to talk to one another. They're as antisocial as you can get. So that'll unfold a little bit more. So let's see how it goes. Okay. So, right. Now, so let's elaborate on what we just said. So, we have defined classical light as equivalent to saying that we have a statistical mixture of coherent states. Now, why was that a meaningful definition? Well, really that came from whether certain measurements that we do on the system have a classical description. That's, in my opinion, what makes something meaningfully classical. Can you describe the measurement outcomes from a classical random model? Or are you required to somehow go beyond classical statistical prediction? Okay, so the operational definition measurement outcomes are predictable from a classical statistical theory. So what kind of measurements were we talking about? Well, the measurements that led to this definition were photon counting. Right? So if what we thought about was, well, let's think about photon counters. We have some number of them. We have some intensity coming into each of these detectors. And detectors. We might look for counts in each of these detectors or some coincidence. And as we discussed last semester, we can understand the statistics of this photon counting from a purely statistical theory of random light coming into this, or purely coherent light coming into this, where all the randomness in the photon counting was due solely to the matter. It had nothing to do with the light whatsoever. And the way we saw that is that from the Glauber theory, this coincidence rate depended on these normally ordered products of intensities, operators. So that's my coincidence. And, this was equal to, some sum over all the modes, some constants, and then, a dagger for mode 1, a dagger for mode 2, dot, 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 a dagger for mode n, a1, a2, dot, 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 an. That was our normally ordered product. So this was predictable from a classical theory. That's to say that this was the same thing. This is equal to the, all those stuff out front integral over all the modes times a classical statistical function, a probability distribution, a positive function, which can be normalized, times, the intensity of mode 1, intensity of mode 2, dot, 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 n. That's to say, this was a statistical average of, e squared 1, e squared 2, all the products of the intensities. So my photon counting could be predicted from a purely classical statistical theory plus the intrinsic shot noise of the detection process if the state of the light, so this is equal to that if rho was expressible in terms of a convex combination, a statistical mixture of coherent states. With this, the so-called Glauber-Sudarshan probability distribution greater than 0. So if the state has this, it can be represented in this way, with this being a classical probability distribution, then photon counting can be described in the semi-classical theory. And so we call that classical light. Moreover, we showed that such states arise from classical statistical current. So it seemed like a good definition. But it's not the whole story. Because as we just saw, we could choose to detect our field in a different way. Suppose instead of doing direct photon counting, I do homodyne detection. And I want to ask, is my homodyne detection describable from a classical statistical model in the same way as direct photon counting is? It's a reasonable question to ask. So, we could consider homodyne detection. In which case, for example, we measure, instead of the photon number, we measure quadratures. Okay? So for example, if I wanted to ask, is there a classical model that describes what I expect to see statistically for the square of the x quadrature? Well, that is equal to a plus a dagger over root 2 squared, which is a squared plus a dagger squared plus a dagger a, but plus a dagger. So this is not a normally ordered product of a and a dagger. It's a symmetrically ordered product of a and a dagger. So quadratures don't, measuring quadratures isn't the same thing as measuring photon counts. In fact, we know, for example, from quantum mechanics, I could write this object as the integral, this is the x representation, the square of the wave function. If I had an x representation, right? And this, for example, for a squeezed state, the squeezed quadrature, this is a Gaussian. And this distribution is positive. Even for a squeezed vacuum.
This will always be positive.
It will be. Yeah. But I just want to emphasize this fact that the fact that even if we're below the vacuum level, that doesn't, there's a perfectly classical statistical probability distribution that I would sample from. Get this, positive.
What makes that classical?
Because I can make predictions of what I'm going to see from a purely classical statistical theory. There's no quantum interference that would ever say I can't. Now, of course, I can't. It's not fair to do this just for one observable. That doesn't tell the whole story, right? Because of course, if you do for X, you might not be able to do it for P simultaneously. What we want to get at, as we're going to develop this a little more, under what circumstances can I explain the whole experiment in terms of flipping coins and use classical logic if this is true conditional probability distributions. If I can do that, then for all intents and purposes, it was classical. But beyond this somewhat slippery question of what is classical and what is not classical, what this illustration shows us is that it's not just about normally ordered products. That if I want to think about characterizing the state of light, I should think more generally. It's not just about the Glauber P representation. Now, why is that? Why is there some freedom at all in how I represent the state? Well, that's because we're thinking about so representations in terms of coherent states are not unique. What do I mean by that? Well, the coherent state is a kind of strange state. It's not an eigenstate of an observable. It's not an eigenstate of a Hermitian operator. The coherent state is a phase-space eigenstate. That's to say, it's an eigenstate of some combination of X and P, not just X or P alone. And this is non-Hermitian. And so these are not orthonormal. This is not an orthonormal basis. We know that the eigenstates of Hermitian operators form an orthonormal basis, but not of non-Hermitian operators. In fact, we know that the set of states is not a typical basis. The states are non-orthogonal. Their overlap is non-zero. Depends on the Gaussian fall off, but it's not zero. Alpha does not, no matter how big it is actually, not zero. And it's over-complete. That's to say, as you proved, the integral over all the projectors is 1, but I could also, but this is a bigger set than's necessary. I can remove some of these and still get a complete set. It's over complete. So this is kind of a weird basis to work in. And what it means is that we're kind of simultaneously trying to represent the state in X and P at the same time. And because of the incompatibility of X and P, there's something odd about that. Okay? So, let me just remind myself one more. Sorry, I gotta bring my notes up. Right. Yeah. Okay. So let me just conclude this lecture with the following. So the way in which we are trying to represent our states in terms of coherent states is equivalent to trying to doing quantum mechanics in phase space. Now, that has a long history. It was been approached for decades from many different perspectives. One of them had to do what we just discussed, Glauber and photon detection theory and all of that. But clearly this is a problem that's, you know, it's bigger than quantum optics. I mean, it's not much bigger than quantum optics, but this problem is bigger than quantum optics. Because, of course, we can think about the deep question of the incompatibility of positional momentum is kind of the heart of quantum mechanics. So how we describe quantum mechanics in a phase-space setting seems like a pretty important problem and has been long studied. In particular, what we know is in order to think about quantum mechanics in phase space, we want to understand is how is it different from classical mechanics in phase space? Okay? So what's classical mechanics in phase space? Well, we could formulate that in a classical statistical theory through the Liouville formulation. So in the Liouville formulation, we say the following. We have a classical statistical probability distribution on phase space. Okay, it's called a script W. It's a function of the canonical coordinates. We'll call them Q and P. Okay? So this represents the state. It's our knowledge of where the system is in phase space. Typically, we talk about a point in phase space. Of course, that's a pure state. That's perfect knowledge of where it is, but I generally don't have that. In classical mechanics, Hamiltonian mechanics tells me how to evolve this state. So my state evolves as a function of time dynamically. And how does it evolve? Well, it evolves as follows. The time evolution of the state, or the probability distribution of phase space, is equal to minus the Poisson bracket of H with the state, which is equal to the sum over all the canonical coordinates, the partial of H with respect to Q, partial of W with respect to P, minus the partial of to P partial of W with respect to Q. That is known as the Liouville equation. So, under the Liouville formulation of classical mechanics, what we have is dynamics, in this case Hamiltonian dynamics, generated by the Poisson bracket, and I have observables I'll call them F, which are functions of the canonical coordinates. And I could then ask, for example, what is the expected value I'll see for my observable at some time t, and that's the average over the distribution for the n degrees of freedom of the distribution on phase space times the observable. Okay? So let me conclude with the following statement. What would we like? This is the classical formulation of the state, of course, evolves as a function of time, and it evolves like this. Okay. So what would we like the quantum mechanics to be? Well, so the quantum mechanics. Well, if I had an observable O hat, which is a function, I'll call this O sub x, which is a function of, let's just say x, one variable. Well, then we do have a formulation like that. We have the wave function, right? The wave function evolves as a function of time. And my expected value of O is equal to an integral of a probability distribution over x of f evaluated at x. Looks just like that, where this is equal to the square of the wave function. If I have an observable, I'll call it O sub p, which is some function of p, well then we also have a formulation like that. We have the momentum space wave function, which is, of course, the Fourier transform. And my expected value of my observable is just the integral over a different probability distribution, P sub p, times my function of p. This is the square of the momentum space wave function. However, if I have an observable which is some function of both x and p, and I wanted to look at what is the expected value of this thing, what I would like is that this thing is some average over a space distribution times the function evaluated at the values x and p. Now, clearly, I can't do that. If I could do that, if this were, then I would say that classical mechanics equals quantum mechanics. QED, see you later on that. The point is that this doesn't work, at least not always. But when it does, if W is a classical probability distribution, then it's equivalent to this. And this thing, though, what we can show is that we can do this if this is what's called a quasi-probability distribution. In other words, as we will show next lecture, we can always do this But this function isn't necessarily a positive function. It'll be negative. It'll be real if this were a Hermitian operator. And so this is a real function. But it can be negative. And that negativity is a sign that of non-classicality of the state. Because it's no longer just, flipping coins. I couldn't get it that way. This particular function isn't unique because it depends on what order I put x and p. Because x and p don't commute with one another, we will see that there's not a unique assignment of this. And they have various names. There's the Husseini function, there's the Wigner function, and there's the Lauer function.
Is there any condition on the f? So what would you like f to be? I mean, the assignment of f, of x and p, based on the operator.
Well, so the idea here is that, as we did in this case, we just replaced the operator by the value x.
Regardless of the, whether it's a normal.
Sure, so we're going to have to get to that stuff. So in this case, this was literally, but as we'll see, that for a particular ordering, there is a particular function, and this is the opposite. But that's for next time. So what we're going to talk about is quantum mechanics in phase space. It's a general problem, but it has applications here in quantum optics because of the relationship of the quadratures to positional momentum and the representation of light in terms of quasi-probability distributions on phase space and the questions of non-classicality. So that's where we're headed. So that the material response is proportional in some way to the fields. Okay? So we can look at the same kind of situation that we did classically, but now with the quantum operators. So let's look at linear optics, expressed in this way. So my positive frequency component here if I want, well, let me write it out. I don't know how to say this. Let me just write it roughly for the moment. I'm being vague about whether this is in frequency space or in time space. Okay? But that's basically what we got. Okay. Now, remember, so my positive frequency components here, let's get rid of the meat here. Let's write this out as we had before in our quantization volume. And again, let me just ignore for the moment, although we really can't. It's important, as we saw in phase matching and the whole shebang, the vector nature of the field. But to get some of the key ideas, I want to ignore that for the moment. Okay? So allow me that. All right? So that's my positive frequency component. It involves the annihilation operators. And the negative frequency components involve the creation operators. Okay? So now I plug that in here. What I see is that, again, I keep in the linear optics, everything is at a particular frequency. So this is really, for each mode, there's omega at that frequency, and there is a chi at that frequency, pardon me. And I'm going to get things like a dagger here and a here. Here I'll get a dagger and an a here. But of course I can then just commute it and that's just a constant, and I don't care about it. So at the end of the day, for linear, and there are two vectors here, so if we have inversion symmetry, this is not going to fly. So, for example, a gas of atoms doesn't have a chi2 response, has a chi3. And that's what we often live off of. What Andy's going to live off of for his thesis. But a crystal that's doesn't have inversion symmetry can have a chi2, and that's the strongest nonlinear effect if you can get it. Right. So if in the linear optics case, again, this is just kind of a schematic. Really, we should look at this in the this is really an expression in the frequency domain, not in the time domain. So in the frequency domain, the polarization density that oscillates at frequency omega is proportional to the electric field at that frequency, with the proportionality constant being chi1 susceptibility, right? If we go beyond, so in that case, as we know, that if you drive the system at frequency omega, it will, in steady state, radiate omega. So in linear optics, you don't generate any new frequencies than were already present. Okay. On the other hand, if we have nonlinear effects, we do get other frequencies, or we can, and even in steady state. And so the process that we were looking at involved when you have a chi2 type nonlinearity. If you look at two powers of the electric field at frequency omega and omega 1 and omega 2, the beat between them can produce another frequency that's either the sum or the difference between those. So that ends up being what we call a three-wave mixing process at frequencies omega 1 and omega 2 and omega 3. So if we call those three frequencies as such, so that omega 1 plus omega 2 equals omega 3, then we can look at the interaction between three waves that have those frequencies. We treat them as plane waves with slowly varying modulated amplitudes. Okay? And we derive from the Maxwell's equations what the equations for propagation of those amplitudes were. And there are all kinds of different nonlinear processes that can come out. For example, if we inject the two frequencies omega 1 and omega 2, then we would generate the sum frequency. If I injected the frequency omega 3 and omega 1, and this was satisfied, then I would generate the difference frequency. And as we discussed, it was important in order for this process to be efficient in the transfer, as efficient as it can be, in the transfer of energy between these waves, that we had this phase matching condition. That the wave vectors also added together, and that was tricky business. We'll come back to that. So one important process, one that we're going to return to in a few weeks, again, we'll talk about more also today, is this process of optical parametric amplification, whereby one has a strong pump field and one wants to amplify another field by transferring energy from the pump into the signal. Okay? So I inject the pump and the signal, and if I satisfy these conditions where omega 3 is now the pump, omega 1 is the signal, then I will have and I choose this to be the case, then I will generate another, I will both amplify the signal as well as generate a new wave at the wave vector propagating direction ki, which is the difference between k pump and k signal, and whose frequency is the difference between this and this. Okay? And that is what's called parametric amplification. Okay?
And the choice whether you get a sum or difference depends on the angle in which you...
No, so it depends what I input, right? So if I put in both of these, but not this, then I generate the sum. Okay? If it's the case that there is, I mean, I have to phase match, and as we said, that required, you know, in this case, well, so it depends on those directions and how the indices of refraction at those frequencies for that direction of propagation, for that polarization, etc.
So the phase matching determines...
It does.
Okay.
Right. Okay. So that was our nonlinear optics 101. Maybe 101, maybe 102. I don't know how far we got. So what we're really interested, the reason for doing this was to understand the quantum optics of this, not the classical optics of this, necessarily. So let's look at the quantum problem now. Get some chunk that will be visible. All right. So, quantum version. So our Hamiltonian for the problem now as a quantum Hamiltonian has the form, if we treat our current as the dipole current, so that's like a minus d dot e, in this case polarization. All right, that's our fundamental Hamiltonian, where these are now quantum operators. And the resonant pieces of this, the pieces that will have the strong, it's a kind of a rotating wave approximation, involve the matching so that all the frequency, we don't have fast oscillating terms. So this is the rotating wave approximation that we've discussed before. Okay. Now, so let's look at the situation where we've driven the system into steady state. So we were beginning our discussion of how we generate what we call non-classical light. And what we said, the way we've defined classical light to this point is light whose state is describable as a statistical mixture of coherent states. And such fields arise from sources if the quantum fluctuations of those sources are negligible. And we treat them as just a mean field, a classical current. And so we needed to get beyond that somehow. And one way to think about that is what are the kinds of currents that are produced in nonlinear optics. Okay? So in order to discuss that, we just began by introducing the ideas of nonlinear optics. And what we're looking at is a situation in which we have some material, we have some dipole response, and that dipole response is no longer describable by the Lorentz oscillator model. Okay? Lorentz oscillator model is a charge on a spring. If you pull the spring hard enough, it's going to be nonlinear. Okay? Of course, so that's why nonlinear optics was developed concurrently with the invention of the laser, because when you had intense enough fields, you were distorting the material enough for the material to have a nonlinear response. Okay? It's strong, but it's not necessarily that strong, and so generally we look at the dipole response in a power series in the amplitude of the field. So we talked about there being a first order response we call chi1, a second order response chi2, chi3, et cetera, et cetera, et cetera. I mean, you would expect these coefficients, if we're in this perturbative regime, that these higher order effects become increasingly less and less important. Now it turns out that for reasons that are not clear in the way I've written it, chi2, although it would be the first nonlinear effect, in order for the materials that have a chi2 response, they can't be inversion symmetric. There's a parity symmetry because of the fact that really this is a vector